It's very important to be able to distinguish linear versus nonlinear functions from each other in word problems. The first one here says, which situation can be modeled by a linear function? Since it's a linear function, we're looking for the situation that's constant rate of change. That's the main concept. So choice 1 says the population of bacteria triples every day. The key word there of triples tells me that it's not a constant rate. Whenever I see the word triples, I'm thinking of exponential. Choice 2, the value of a cell phone depreciates, another key word, at a rate of 3.5% each year. That keyword depreciates is only utilized with exponential situations. Choice 3, an amusement park allows 50 people to enter every 30 minutes. So right there we can sort of see a rate happening. Every 30 minutes, 50 more people can enter the park. So I'm seeing a constant rate going on there, so that's making me think that that's the linear situation. Just to check, choice 4, a baseball tournament eliminates half of the teams every round. And the key word of half, just like if I saw the word double or triples, if I see the word half, that's a decay situation of exponential. Therefore, the linear case here would be choice 3. Which scenario would represent exponential growth? So I'm looking for the one that doesn't have a constant rate of change. Number 1 says a water tank is filled at a rate of 2 gallons per minute. Right there's your slope, or your rate of change. So that's a constant rate of change. Every minute you get 2 more gallons of water. A vine grows 6 inches every week. Every week, 6 more inches are added to the vine. That's another situation where you have a constant rate of change. So that's linear. A species of flies doubles its population every month during the summer. Doubles implies that there's no constant rate of change. And that's a key word for exponential growth. So that's going to be the choice. But let's just check 4 to be sure. A car increases its distance from a garage as it travels at a constant, right there's a key phrase, speed of 25 miles per hour. Every hour they go 25 miles. That's a constant rate of change. That's linear. The exponential case here is choice 3. And one last area that I would like to cover would be the formula for exponential growth and also for decay. Starting off with exponential growth. With exponential growth, you're going to have an output y, and it's going to be equal to a, which would be the initial amount that you start with, times b to the x power. A would be the initial amount you start with, b would be the base that we're working with, and then x would be the power. And many times x represents the timing. However, we're going to be looking a little bit closer at what that base is all about in the context of a formula. You would have y is equal to a times, let's say you had 1 plus r, where r is the rate at which something is growing, because you have to consider that too. And then we're going to raise that to the x power, and in this case we're going to let x represent the timing. So it's important to realize how a represents your initial amount that you start with. The r would be the rate of increase, the rate at which something is growing, and then you have x, which would represent your time. And all that's going to lead you to the y value, which is your output. So this would be the new amount. You have a, which is your initial amount, and then after all the growth happens, you're going to have your y, which is your new amount. So I'd like to look at a word problem that involves this. Anne invested $1,000 into an account. And when you invest something, it's going to have an interest rate. With an interest rate, and it's going to change based on the bank. The interest rate that Anne's going to be investing this with is 2.5% annually. Which is your annual interest rate. So 2.5% is your annual interest rate. She made no deposits